Hello. Finally, we're at trigonometry. It's probably the best part of the geometry class. This whole chapter will be trigonometry and, well, stuff related to trigonometry. If you're wondering, trigonometry is extremely important. The areas in physics where you use trigonometry it's pretty awesome, really. When you're analyzing forces, for instance, you've got something like this laid out here, and then you've got a support, and then you got a cross piece, and you're wondering how these, I didn't really mean to make this look like a gallows. Anyway, you'll use trigonometry to actually analyze the forces on these parts. Well, that's kind of static. On the other hand, if you have something shot out of a cannon, you can use trigonometry to break up the components of motion of, say, a cannonball that's, I guess it was fired near a cliff, dropping it down onto some boats in the bay there. Also in electronics, you have waves. And guess what? Trigonometry is also used to model these waves. The functions you cover in trigonometry get used all over physics and engineering. Lots of different ways. It would take the whole video to list all the things that trigonometry gets used for. So let's just say it gets used a whole bunch. We start studying trigonometry with the Pythagorean Theorem. I think you could say trigonometry is pretty much based on this right here. This is Pythagoras' theorem. These are called legs. And this is going to sound like review to you. I think you've run across Pythagoras' theorem before, and you understand the nomenclature. We're just going to review it and then work some problems using Pythagoras' theorem. Well, these are the legs here. These are the ones adjoining the right angle. Opposite the right angle, that's the hypotenuse. And Pythagoras' theorem is the sum of the squares of the legs equals the square of the hypotenuse. Or, in English, a squared plus b squared equals h squared. Now, remember back when we showed the triangle inequality? Don't get these things confused. It's certainly true that a plus b is definitely greater than h. No way around that. In fact, b plus h is greater than a. That's our triangle inequality. But these aren't squares. If we square these, you have a different situation. For instance, if I put numbers here, this leg is 3, this one's 4, then the hypotenuse would have to be 5. That's not intended to be h5, that's just the length of 5 for the hypotenuse. Well, 3 plus 4 is greater than 5. However, if we square them, we get 9 plus 16. Well, that's 25. Well, 5 squared is 25. So when we square these things, we get an equality. If we don't square them, we get an inequality. So don't get these two confused, and don't get confused as you remember the triangle inequality and say, well, wait a minute, if this is bigger than this, why is this equal? Well, the numbers themselves and the squares of the numbers are two different things. How do we know this is true? Well, there's different ways in different books. You know what Pythagoras did? And I might be able to do it with the computer. I'm going to see if I can make it work. What he did was, he completed these squares. He drew a square here. Let's see if I can sort of give you the idea. Pretend this is a square here. And then he drew another square here. And then he drew this square. Well, the area of this square is, of course, b squared, right? It has side b. The area of this is a squared. And what he did was he just created these squares out of tiles and then took all the tiles and showed that they fit right into this one. And this, of course, has side h, and the area of this is h squared. So he, in a sense, physically showed that this squared plus this squared is this squared by breaking these up, these two areas, and fitting them inside this one. I don't know if we can do that or not. Let's check it out, see if we can. Well, here we have our right triangle, and then we just completed the squares. And each of these squares has one side equal to the side of the triangle, the right triangle. And the point is that this area plus this area should fit right into this area. That's what it means. We have a squared, b squared, h squared over here. So does it work? Well, it's kind of sloppy. I moved this over. I'll show you. We can put this in here. Now we can break this up into triangles and stick them in here. Unfortunately, I had to use the freeform selection tool with a hand that's about as steady as a cork in the ocean. But you get the idea. If we pull out one little corner here and stick it in there, and pull out some more, and we put it in there. This fits in there, and what's left over? The blue and the yellow will exactly cover the square that we created with the hypotenuse. Naturally, you see some blank spots and that. Sorry, like I said, the freeform selection tool was a little bit rough. And this software isn't really the best for what I was doing, but you get the idea. And this is kind of what Pythagoras did. That's exactly what Pythagoras did. He created these squares over here, another one over here, and then took them apart and showed that they fit right inside here. And that's the same as saying that a squared plus b squared equals h squared. So, let's just work some problems. You'll get much better with the Pythagorean Theorem as you work problems with it. Here we have one of those what's the mistake problems. Well, let's see here. A squared plus b squared equals c squared. And I usually write h squared to indicate that this c is in fact the hypotenuse. Well, let's see, that would be 24 squared plus 10 squared. Oh, wait a minute here. 10 squared plus, oh, I see. Well, they confused the leg with the hypotenuse. This should be 10 squared plus 24 squared equals 26 squared. Other than that, everything's fine. I don't know if this is a common mistake or not. Most students recognize that the legs are the ones adjacent to the right angle, and the hypotenuse is opposite the right angle. But I suppose it's a possible mistake. Okay, here's a similar one where, let's see here, the Pythagorean Theorem is certainly set up right. X squared is the hypotenuse, x squared equals 7 squared plus 24 squared. And 7 squared plus 24 squared equals 7 plus 24 quantity squared. And that's not right. You definitely can't do this. This does not equal this. Let's lay it out just to make sure you see what's going on here. A plus b quantity squared. That's a squared plus 2ab plus b squared. That is definitely not equal to a squared plus b squared, is it? Nope, not even close. You got this little problem right here. Without that, you'd have it. But the fact is, you do have this, and they're not equal. You can't square the sum and say that that's the same as squaring the individual components of the sum. That wouldn't make any sense at all. If this were true, think of it this way. 3 is 1 plus 1 plus 1. Suppose you square that. Now, if you're going to assume that that's the same as taking 1 squared plus 1 squared plus 1 squared, well, 1 squared is 1, 1, 1. That equals 3. But if you add these up, 1, 2, 3 squared, that equals 9. So there's a huge difference. You can't just bring your exponent inside and apply it to each component individually. That's right out. Can't be done. That's what this person did, and that's all wrong. Now this one, it should be pretty simple. We just have to find h. Well, we can use the Pythagorean theorem. This h here, I don't like that. I mean, we're using the Pythagorean theorem. Why use h for an altitude? I guess some people do, but I don't like it. Let's say a for altitude, okay? That way we can call this h. And why don't we call this one b? That'll be just like our original writing of our Pythagorean theorem. A squared plus b squared equals h squared. But in this case, b is half of 32. Remember, with an isosceles triangle, the angle bisector cuts the opposite side into two equal segments, two congruent segments. Or to put it another way, the angle bisector cuts the opposite segment into exactly the same ratio as the adjoining sides. And since the adjoining sides are in a 1-to-1 ratio, then these two segments must be equal. We've done this before. So this side here, this b, is 16. So what we have is 16 squared plus a squared equals 20 squared. And what we're actually looking for is a, not a squared. So in the end, we're going to have to take the square root of this stuff. That's what a equals. And so with Pythagoras' theorem, we can lay this out, pardon me, and get that a equals 12. Well, that's part of the problem. What we need is the formula for the area. Remember, that's 1/2 base times height. And in this case, that's 1/2. Remember, the base for the triangle is 32. And the height we have just computed as 12. can do some cancellations and a little arithmetic and get, and this all works out to 192. And that is your answer. That's the area. Yipes, I used area and area for altitude. Well, sorry, too many things starting with A, I guess. Maybe I should write area A sub t as, there we go. But then it could also be altitude of the triangle, couldn't it? Well, sorry guys, maybe I should have used something else for altitude. A sub t, area of the triangle, is 192, and altitude was 12. Now here's one, which frequently I draw a picture so we know what we're doing here, but gee whiz. They say it's a right triangle. We know what they look like. And they're giving us the lengths of the legs. And you should probably be able to remember Pythagorean theorem without actually looking at a right triangle. A squared plus b squared equals h squared. So this is going to be easy. We're just going to write 8 squared because they gave us the legs. If they had given us the hypotenuse and asked for one of the legs, we just have to rearrange the equation. It's still not that big a deal. And 15 squared, well, that equals h squared. And that, I think, would be 64 plus, is that 225? I'm going to have to check that. Yeah, 15 squared is 225. So we add this up and get 289. But that is h squared. H would be the square root of 289, and my calculator tells me that is 17. So, yeah, correct answer would have been B over here. 17 inches is the hypotenuse. And here we have to find the value of the unknown side length. Actually, they said find the unknown side length. Well, there it is. Well, done. Let's do the next problem. I don't think that's what they meant. I think they actually wanted a number to go with this. Let's see here. What do we got? Well, we got all these little lines here telling us that these segments are all congruent. That means this is 11 over here, and this is 11. Well, then this length must be the square root of 11 squared. Yeah, let's not do that. Heck, you're all sophisticated math types by now. You must recognize that 11 squared plus 11 squared is 2 times 11 squared. That is x squared. So, doing it that way makes it a bit easier to take the square root. It's not obvious what the square root of 11 squared plus 11 squared is, but it is obvious that the square root of 2 times 11 squared, let's just write it out here, that's supposed to be an 11 squared. Well, that's just the square root of 2 times 11. And in fact, that is the answer. Root 2, you should parentheses around the 11, so it makes it obvious. So my 11 looks like 2 parentheses. There we go. Root 2 times 11. That's what x is. 11 times the square root of 2. It's pretty easy. Just had to recognize this congruence thing going on here. Well, for this one I did go ahead and draw a small picture so we can see what it is we're doing. We're looking for the area of a right triangle. Well, for a right triangle, the altitude is just this leg right here, which we don't know yet. Well, one of the legs is 15 feet. We could have made this one 15 feet and said that we didn't know the base. but one of them we don't know. It's either the altitude or the base that we don't have. But they tell us it's a right triangle. So that helps because we do know the hypotenuse. And if we call this x, well, we can start with our Pythagorean theorem, of course. And that equals 39 squared. Or x equals 39 squared minus 15 squared. And we'll take the square root of that. Now we set this up from the Pythagorean theorem, which leads to this. 39 squared is 1521, 15 squared is 225. We get the square root of 1296, which is 36. Now we know that x is 36. Well, that's not exactly what we're looking for, though, is it? Now we need a little more room, so we can use 1/2 BH, which will be 1/2 times 15 times 36. And if you're wondering, yes, I got the proportions very wrong here. This should be like less than half as long as this. And this turns out to be 270. That one up there. Your answer would be A. Most of this problem is over here. You had to find this leg here. Once you got that, it's pretty easy. Here's one where they give us the dimensions of a right triangle, but only in terms of x. And they want us to solve for x. So naturally, what we're going to end up doing is setting up an equation where this squared plus this squared equals this squared. And if the squared terms don't drop out, we'll solve a quadratic equation. If they do, well, then we're lucky. We'll only have to solve a linear equation. Let's see how it works out. So when we lay this out, we don't get the simplest equation you've ever seen, but that's okay. As long as we've got it right. We got 2x plus 4 quantity squared plus 2x quantity squared is equal to 4x minus 4 quantity squared, which is the same as 4 times x minus 1 quantity squared. This part reduces to 4 squared is 16, x minus 1 squared is x squared minus 2x plus 1. And all this we can rewrite as 16x squared minus 32x plus 16. Now, over here, 2x plus 4 quantity squared, that's 4x squared, plus 2 times 2x times 4, which is 16x, plus 4 squared, which is 16. And of course 2x squared is just 4x squared. So we can start combining some terms here. This should be 8x squared, right? 4x squared. And we still got 16x and 16. Well, how about over here? Boom. We can subtract 16 from each side and get rid of those. So, when we lay out this equation, we get this. The 16's cancel. If you saw a jump, it's because I rewrote this. I thought I made a mistake. It turned out I hadn't. Well, that's the way it goes. The 16s cancel. And over here, I can subtract 8x squared from each side and get an 8x squared over here. I can add 32x to each side and get 48x here. When I rewrite this, I get 8x squared minus 48x equals 0. Now, we just use our distributive property to pull out of as much as we can. We can put an 8x out in front here. And that leaves us with x minus 6. And as you remember from algebra, the only way this could be 0 is if x equals 0 or x equals 6. Well, if x equals 0, we wouldn't have a right triangle, would we? I mean, there's nothing up here to prevent x from being equal to 0. Well, actually, I guess there is, because that would make the hypotenuse equal to minus 4, and that also wouldn't make any sense. So there's a couple of good reasons that x equal to 0 is not a solution. However, x equals 6, well, that should work. I mean, there's nothing illegal about it. It doesn't lead to anything strange. What about this? If x was 6, this would be 12. Well, this would be 12 and 4, that's 16. And this would be 24 minus 20. Is that right? Yeah. So we got 12, 16, and 20. Well, do these make sense? Could this be a right triangle with dimensions 12, 16, and 20? Remember the 3, 4, 5 triangle I told you about, and all multiples? Well, suppose we multiply everything by 4. 3 times 4 is 12. 4 times 4 is 16. 4 times 5 is 20. So that 3, 4, 5 rule, remember, you can just multiply straight through. So we've got 3, 4, 5 is a basic, well, they're called Pythagorean triples. Any multiples of these, as long as they're the same. So I can write k times 3, k times 4, and k times 5. Those will always be legitimate dimensions for a right triangle. So I just use that as a check. They didn't ask us to do that. They just want us to find x, and the answer is actually 6. But all this stuff, this is just to check and see if our answer actually makes sense. And it does. This is a Pythagorean triple. Therefore, it's a right triangle. There's nothing contradicting anything in this. Well, here's one that's, well, it's tempting to try to find ratios, because that's what we were doing all in the last chapter. I think that it'd be nice if the altitude broke up the opposite side into segments that were of some ratio that we could use to find out what these two segments are. But if you look for that, you'd be spinning your wheels, because there just isn't any postulate or theorem that tells us how an altitude actually breaks up. It could break it up anyway. We don't have any way of knowing about the ratios here. Which means, if we're going to use this leg here as part of our Pythagorean theorem to find x, or this leg, we need to figure out what they are. All we know here is the total. Well, there's a way we can do this, but now we have to go backwards. We've got one unknown. We've got to introduce another unknown, which is kind of like going backwards. First, there's one thing we don't know. Now we're going to have two things we don't know. What we're going to do is we're going to call this small section here y. Well, we're going to call this section here 14 minus y. You see, even though we don't know what these two segments are, we know something about them. We know they add up to 14. And we have two right triangles here. This is a right triangle also, and this is. So we can generate two equations and two unknowns and hope that something will pop out. It will actually come up with solutions for each of these variables. So let's try it and see what the heck happens here. Well, this isn't too bad. With this we get... So what we can do is write down two equations, both based on the Pythagorean Theorem. X squared plus y squared equals 13 squared, and here 14 minus y quantity squared plus x squared equals 15 squared. So I've got this set up here. Now, if you can drag your brain all the way back to somewhere around the middle or second half of last year's algebra class, you might remember that when you've got something like this, these two equations, you can actually add or subtract one equation from the other. It's really just a combination of the addition property or subtraction property of equality combined with substitution. For instance, suppose I set this whole thing equal to, let's say, a for the moment. These two are equal, and they're all equal to a. Well, I can add a to both sides, right? So suppose I put plus a here, and plus a over here. Well, that's legal. We just use our property, addition property of equality. Although, I think I made one mistake. Hold on a minute. Let's use our subtraction property of equality. That'll work out better in the end. Now, a equals 13 squared. So I can substitute 13 squared down here for a. Just cross that out. Minus 13 squared. But over here, I could also substitute 13 squared in here for a. But I don't have to. A is also equal to x squared plus y squared. So suppose I substitute that in here and get minus x squared minus y squared. And cross out that a. If it seems odd to you that we substitute 1 equal, we've got two expressions that are identical, they're equal. Which one I choose to substitute, it's entirely up to me, or entirely up to you. You're free to choose whichever way makes it easier for you. In other words, use the rules of mathematics, the postulates, the theorems, everything you've got to make life as easy as possible for yourself. That's the whole point of mathematics, and if you do it the easy way and make it easy for yourself, you will get at least full credit, because that's what you're supposed to do. That's what mathematics is all about. It's about taking really complicated things and turning them into reasonable equations. Since it works out better for us to substitute x squared minus, well, x squared plus y squared in here for a, and 13 squared for a, that's what we do. Always use the rules to your advantage. And being high school students, I'm sure you know how to do that. You do it every day outside of mathematics. Now just apply that same cunning you naturally have as a high school student to mathematics. Now if we do this, if we were to subtract this expression from this side and this expression from this side, what do we end up with? Well, we have to expand this. Well, if I expand this and then include the fact that I subtracted this equation from this equation, well, the expansion of this is 14 squared minus 28y plus y squared. Sure you remember that from your previous algebra class. And then we're going to subtract x squared and y squared. That's going to work out real well, because we got an x squared here, and it's going to drop out. That's lucky. Well, we've also got a y squared, so we're not even going to have to solve any quadratic equations. As a matter of fact, we're down to one expression with a y in it, and all the rest are just numbers. Oh, we're pretty good here. This is going to be easy to solve for y. Once we've got y, we can put it in and solve for x. And now all we have to do is rearrange what's left over here. Put 28y over here. Subtract this stuff, and we get 14 squared minus 15 squared plus 13 squared equals 28y. This is 196. This is 225, and this is 169. And if you do the arithmetic and then divide by 28, you get that y equals 5. So we're going to put that in over here. We wanted to solve for x. Well, now we can do that pretty easy. Let's just give ourselves a little bit more room here, and we're almost done. We have that 5 squared plus x squared equals 13 squared. Or, well, let's write it out. Okay, 5 squared plus x squared equals 13 squared. And let's not confuse any of this. This is where we found y. Now we're going to find x. And we have that x squared equals, well, that's 169 minus 25. And that's 144, but 144 is just 12 squared, right? X squared is 144, so x equals 12. We can put that in here, and now we've found everything. There is one very interesting thing about this problem that you can think about. We just found the altitude here. That's what x is. We already knew the base. So what's the area of this triangle? Well, it's 1/2 of 14 times 12. And that's, what, 84? And that equals the area of the triangle. Well, look at that. All we knew was the 3 sides to begin with. We didn't know any of this. We didn't know the 12. We didn't know the 5. All we knew was the 3 sides. And we managed to figure out the area from that. The problem didn't ask you to do that. It just asked you to find the altitude. But once you've got the altitude, you can find the area. Which means that if you don't know anything except the length of these 3 sides, there is a way to find the area. And in future sections, we'll get to a more compact formula. You can do all this stuff, but all this stuff will reduce to an equation we can use to compute the area when we don't know the altitude, but we do know all 3 sides. That's about it for now.